Okay, first of all, many thanks to the organizers. I'm both pleased and honored to be here. And I would like to make just a few remarks before I start about some choices about the content. The first point is that I will make an extensive use of quotations from Bell's papers. And I do this for two main reasons. The first one is that I would like to push strongly young people to read directly the Bell papers, which are a unique source of inspiring ideas, not only on foundations of quantum mechanics, but also, I would say, on the general epistemology and philosophy of science. And the second point concerning my extensive use of quotation is that, in my view, but I think not only in my view, John Bell should be considered also as a true natural philosopher in the old noble tradition of Philosophia Naturalis. And so in this sense, as always happens when we have to reconstruct the thought, the views of a philosopher, some sort of textual analysis is indispensable. So in this sense, it's useful to recall the direct text passages. You will find in my presentation also some useful reference, useful to the debate on these issues, so that if anyone is interested, of course, I can send the slides with the references. And finally, contrary to Giancarlo, I will include some stupid statements in my presentation because it's essential to know that these statements are present in the literature, so that we have to be careful about this subject. So it's useful sometimes not only to hear them reported, but also to read such stupid statements.
Some stupid statement that they have
Yeah. Yeah, I will have some 2 or 3 of these stupid statements. Okay, let me come to the brief explanation of the title. The Bell twins refers to the strange situation according to which two very different views of the epistemology of John Bell seem to coexist, to be on the market. There is a Bell number 1 who believes in the plausibility and consistency of a quest for an observer-free description and explanation of the quantum world. But there seems to be also a Bell number 2, which is conceived as one of the major sources of inspiration for the idea that an observer-independent quantum reality has been shown to be untenable once and for all. I will start my presentation very smoothly with a joke, a short science fiction tale. I'm not a novelist, so I apologize in advance, but as I say, it's just a joke. The main character of our story is named Albert. He lives in the future, and he happens to be interested into the history of physics of 20th century. And we imagine that some time earlier, some earthquakes and tsunamis took place, so that a big part of the content of many libraries all over the world have been destroyed, so that people have to rely on the testimonies of some people who wrote things in the times contemporary to the old books that have been lost. We know that this is not new in the history of mankind. For example, in the first centuries of the Middle Ages, this was exactly the situation, for example, concerning the the writings of Plato and Aristotle. So by studying textbooks on his age, Albert came to learn that the rise of the quantum technology was to a large extent due to a smart guy named John Stuart Bell. He happened to read a survived text of the age, and he could learn things like this one. Bell's work, without a doubt, triggered the second quantum revolution, primarily based on the recognition of the extraordinary features of entanglement and pursued with efforts to use entanglement for quantum information. So Albert started to wonder who was this man who made this possible. And first of all, he learned that he wasn't an engineer, but a theoretical physicist. And after that, he learned that one of the missions of this man, this scientist, was to provide mathematically sound proofs of far-reaching claims like the following. Local realism is false. Hidden variable theories cannot exist. If local realism is false, no realism whatsoever in quantum realm can be defended anymore. In support of this interpretation of this that we call the Bell mission, you could find some texts. And in the book dated 2002, which fortunately survived the earthquake and the following tsunami, Albert could read texts like the following. While a very tiny loophole in principle remains for local realism, it is a very safe position to assume that quantum mechanics has definitely shown to be the right theory. Thus, a very deep question, namely whether or not events observed in the quantum world can be described by an underlying deterministic theory, has been answered by experiment, thanks to the momentous achievements of John Bell. So, okay. You see, luckily the whole library of the Vienna University survived, so this was contained in the library. So, Albert was impressed by this weird word, unspeakable, and curious about why the editors of the book had bracketed the un part of the unspeakable. So he started to search after ancient texts that might help him in understanding the issues at stake. So eventually he could find a spare copy of this book, and he started to read the book, and he discovered that he could find no local realism, no hidden variables anathema, no brackets around unspeakable, and so on. So the author of this book, Albert thought, must have been a twin brother of the other John Bell. So this is my less serious part of the talk. As I told you, I'm not a novelist, but it was just a joke to begin smoothly. Anyway, now I'm back to the more serious part of the talk, that I would like to start by referring again to a passage from this text, which is the introduction to the second edition of the collection of Bell's paper called Speakable and Unspeakable Quantum Mechanics. I recall this because curiously, but it's an unfortunate case, this introduction is a mixture of right statements and completely misleading statements, so that must be read very, very carefully, even when he doesn't say clearly wrong statements, like the case here. Why I start from this passage from the aspect introduction? Because one of the most common points when we discuss about these problems is to discuss the relation between John Bell and Einstein on the foundations of quantum mechanics. And it's very common to find statements according to which the Bell's contribution to the foundations can be seen as a disproof of the main foundational positions on the quantum mechanics. And I will try to say in which sense this is only a part of the truth, because there is a sense in which Bell's contributions go into a direction that Einstein wouldn't have liked, but this is only a part of the story. That's why I think the relation Bell-Einstein is a useful place where we can start and can provide a sort of unifying thread to see many foundational important points. Passing, it's worth noting that also Einstein suffered some, what I call here, a twin phenomenon, because there is a schizophrenic tendency to see two Einsteins, the young innovator and thought-provoking, and then the Einstein number two, who is exactly the Einstein who will spend years and years asking questions about the foundations of quantum mechanics. But apart from this, which is not important, of course, the most important part, again, as I said before, I will focus now from some slides on the relation between Bell and Einstein, because, as I said, this relation can provide an interesting and unifying thread on these issues. As I said before, on one side, it can be said that Bell's contributions lead to a direction which is far from Einstein's expectations. And this regards essentially two claims, which I call the pre-existence claim and the locality claim. What is the pre-existence claim? I gave this summary. Standard physical system has at all times a whole bunch of pre-existing properties that are supposed to be encoded in its state, no matter whether there is a measurement interaction or not. Although, as we learn already, and I will come back to this later, this pre-existence claim is not a presupposition in the EPR argument. I think that it can be safely said that Einstein would have longed for a theory that in some sense or another could include such claim among the capacities of the theory. The standard, apparently non-local quantum mechanics does not make room for the pre-existence condition in any sense, was exactly the reason for which Einstein charged quantum mechanics with incompleteness. And on the other hand, Bell was very clear that such pre-existence claim cannot hold in this form in any formulation of quantum mechanics, completed or not completed. And the first ironic point that I would like to stress here is that one of the most common misunderstanding about the Bell's contributions in this field lies exactly in attributing to Bell himself the endorsement of some sort of this pre-existence claim. And we can see how wrong is this attribution. If we think of his first paper on foundations of quantum mechanics, which is the one that he wrote in 1963, but as we know, for editorial problem, was published in 1966, where Bell discusses the several no hidden variables proof in preceding years. And he wrote as follows: these demonstrations require from the hypothetical dispersion-free states not only that appropriate ensembles thereof should have all measurable properties of quantum mechanical states, but certain other properties as well. These additional demands appear reasonable when results of measurement are loosely identified with properties of isolated systems. So in a way which is consistent with this pre-existence claim. They are seen to be quite unreasonable when one remembers with Bohr the impossibility of any sharp distinction between the behavior of atomic objects and the interaction with measuring instruments which serve to define the conditions under which the phenomena appear. This is the first instance, because we will find another instance, of what Abner Shimoni called the judo-like maneuver. So exploit the force of the enemy against the enemy himself. I'm not a judo expert, but this is basically the spirit. So to use the Bohr dictum itself to show in order to show how implausible the no hidden variables proof turned out to be, exactly because they did assume something like the pre-existence claim. So this is one first aspect in which we can safely say that Bell showed that the path imagined by Einstein could not be taken in exactly that way. The second, of course, is the path linked to the locality claim. I stress that here I do not enter into the problem of the several definition of the locality claim. There is a whole literature on that, but I skip that. So we already know very well what the locality claim amounts to, so that no objective property of physical system S can be affected by operations performed on physical system isolated from S, where this formulation is consistent in spirit with the pre-existence claim that we've seen before, where we mean by an objective property a property that satisfies the EPR criterion that we heard about in Tim's talk yesterday. So if without interacting with the physical system S, we can predict with certainty the value Q of a physical quantity Q pertaining to S, then Q represents an objective property of S. Again, that this path cannot either be taken, has been shown, of course, by Bell by his famous theorem. And although, as I write there, the exact nature and implications of these intentions about the original Einstein's idea and the Bell's results, in a way, are still open. Why there's this tension, of course, because we can, if we read this text of Einstein's, this is a text passage taken from a paper, a short paper that Einstein published in 1948, which is called Quantum Mechanics and Reality. It's a very short paper published in a philosophical journal called Dialectica. It's very short, and it's been reproduced by Einstein in a letter to Born, so that it can be found in the collection Born-Einstein letters. It's interesting, in my view, to read this passage. If one asks what, irrespective of quantum mechanics, is characteristic of the world of ideas of physics, one is first of all struck by the following. The concepts of physics relate to a real outside world, that is, ideas are established relating to things such as bodies, fields, etc., which claim a real existence that is independent of the perceiving subjects. Ideas which, on the other hand, have been brought into as secure a relationship as possible with the sense data. It is further characteristic of these physical objects that they are thought of as arranged in a space-time continuum. An essential aspect of this arrangement of things in physics is that they lay claim at certain time to an existence independent of one another, provided these objects are situated in different parts of space. Unless one makes this kind of assumption about the independence of the existence, the being thus of objects which are far apart from one another in space, which stems in the first place from everyday thinking, physical thinking in a familiar sense would not be possible. So it's a quite strong statement. It is also hard to see any way of formulating and testing the laws of physics unless one makes a clear distinction of this kind. So we can see from this statement that in some sense, Einstein is making of this separation principle a sort of condition of thinkability of physical systems in a way. And it is quite clear that the Bell's theorem shows a big tension and the sort of impossibility in those terms of holding such view. So, to repeat again, up to now we've seen very briefly why the claim that Bell's contributions disprove Einstein's view of physical reality are only to a certain extent correct. But what I wanted to stress, and I will stress now, is that this is only a part of the truth. The other part, in my view, has to do with the sort of epistemological affinity between Bell and Einstein on at least two further points. First of all, a general stance of a philosophical nature that I refer to as scientific realism. And I would like to stress that this scientific realism, this term is very dangerous, but nevertheless it must be used because there's nothing better at the moment. As a regulative ideal, in the sense that, of course, I will return to that, it must be sharply distinguished from other kinds of realism that, as we have seen, and we will see again, it's deeply wrong to attribute to the Bell's views of quantum reality. What I mean by scientific realism in this sense, as a regulative idea, I mean that the aim of a fundamental physical theory is to try to describe and explain physical reality and not just the knowledge that we have of physical reality. And I strongly recommend this paper about the kind of realism that has been defended during the whole scientific career of Einstein. This is the first point on which we can find an epistemological affinity between Bell and Einstein. And the second point can be summarized as the plausibility of the search of a formulation of quantum mechanics in which observer-dependent notion should not play a grounding role. Of course, it's perfectly plausible that they appear and they can be rigorously treated in the theory, but they should not play a fundamental role. I think that we can safely say that in these terms, Einstein would have shared this view of the aim of physical theory.
Einstein made it clear, but in his writings, but it's not. In any case, there was a story that I forgot who it comes from. Einstein gave a lecture at Princeton in the early 50s about the situation with quantum mechanics, and he made exactly this point there in that lecture. And this impressed. Everett was there, and this is what led Everett to his own version.
I see. Is it published? Do you know?
This is the lecture itself?
Yes.
I doubt it very much. Whether the story, it comes from somewhere there, that's published. But I can't, now at the moment, I can't remember where this comes from. Does anybody remember?
Okay.
Maybe it's from the biography of Everett by Peter Byrne.
I see. I will check that. Okay, so the main point is here that there is a plausible sense in which realism is a position that both epistemologies of Bell and Einstein would have shared. But of course we have to focus a little bit more and try to understand what sort of realism can be still entertained in this field, and how we should try to make sense of this general philosophical stance on the foundations of quantum mechanics. First of all, we would like to give an example of what should not be done. For this aim, I use this quotation taken from a sort of review paper by Nobel Prize Anthony Leggett, where we read, irrespective of the validity of quantum mechanics or not, what can we say from experiment about the validity or not of the concept of realism as applied to the physical world? Why did I say that this is what should not be done? But at least by a philosophical point of view, the main defect of a stance like this is that it's far from clear what is the general theoretical framework in which the term realism is used. So it sounds very odd to face the problem of realism by stating explicitly that we just rely on experiment in trying to understand if realism can be applied to the physical world, as if there were a sort of theoretical vacuum in which we could check realistic or unrealistic positions. What I find, in some sense, a more fruitful way that I would like to advertise here, because in some sense I find it's been underestimated. Can be found in this book by Arthur Fine, The Shaky Game. Personally, I find this book one of the best books on the Einstein's view of quantum mechanics. I don't know whether anyone agrees on this, but I think that this is a must-read book. Fine has different views on specific aspects, but as a whole, it's a very nice book, and interesting and challenging book. What does he say in this book that is of interest to what I'm saying here? First of all, Fine quotes a letter of Einstein that reads as follows. In this letter is concerned with causality. Einstein says, on this account, it can never be said with certainty whether the objective world is causal. Instead, one must ask whether a causal theory proves to be better than an acausal theory. And this is the Fine comment. The upshot is to move the entire issue of causality out of the empirical realm, where it would be conceived of as more or less separately and directly subject to empirical test. Instead, one gets at the issue of causality by specifying what counts as a causal theory, namely one with non-probabilistic laws, for example, and one replaces questions about whether causality holds in nature by questions about which theory is better. And this procedure is called by Fine in theorizing. What I would like to suggest, basically, is to try to apply this in theorizing procedure to realism in foundations of quantum mechanics. Namely, not to, I say, inflate into quantum mechanics an a priori notion of realism, usually expressed in some sense or another as the pre-existence claim, just to discover that quantum mechanics, of course, cannot host such a notion, but try to formulate and to see whether, or to see how a realistic theory might perform with respect to a non-realistic theory. So we try to try, according to this proposal, to in-theorize realism by constructing realistic theory, where we call a realistic theory a theory which complies with a set of criteria, for example, like the following. The first criterion I call with big effort of imagination ontology. So realistic formulation should clearly and unambiguously posit at the outset the domain of entities endowed with an unambiguous ontological state and which are supposed to be the basic objects that the theory purports to describe and explain. I will formulate basically 3 criteria, and I will attach to each criterion a text taken from the Bell's papers, which in my view supports the choice of this the respective criterion. This is taken from Against Measurement, and basically it's a statement of a general realistic stance which is compatible with this ontology criterion. In the beginning, natural philosophers try to understand the world around them. Trying to do that, they hit upon the great idea of contriving artificially simple situations in which the number of factors involved is reduced to a minimum. Divide and conquer. Experimental science was born. I would say also theoretical science was born. Anyway. But experiment is a tool. The aim remains to understand the world. To restrict quantum mechanics to be exclusively about piddling laboratory operations is to betray the great enterprise. A serious formulation will not exclude the big world outside the laboratory. Oops, sorry. The second, as I said, observer independence. A realistic formulation should not need to assume the necessity of observers for the main properties of the basic objects to hold, though being able to recover observer-dependent notions and results. This is taken from Bielbus for quantum field theory. The usual approach centered on the notion of observable divides the world somehow into parts, systems and apparatus. Of course, there is a considerable overlapping between lectures. I will quote passages which have been already quoted, but I mean, if the net effect is to reinforce good points, why bother? There is nothing in the mathematics to tell what is system and what is apparatus, nothing to tell which natural processes have the spatial status of measurements. It seems clear that in a serious fundamental formulation, such concepts must be excluded. In particular, we exclude the notion of observables in favor of that of beable. The beables of the theory are those elements which might correspond to elements of reality, to things which exist. Their existence does not depend on observation. Indeed, observation and observers must be made out of beables. In this sense, of course, the observational language can be somehow recovered and not excluded at the outset from the observer-independent language. And the third criterion is what I call here non-vagueness. A realistic formulation should make sense at all scales, namely no micro, macro of classical quantum distinction should play any fundamental role in stating the basic principles of the formulation itself. And this is taken from against measurement again. The kinematics of the world in this orthodox picture is given by wave function for the quantum part and classical variables which have values for the classical part. The x's are somehow macroscopic. This is not spelled out very explicitly. The dynamics is not very precisely formulated either. It seems to me that the only hope of precision with the dual psi-x kinematics is to omit completely the shifty split. Let both psi and x refer to the world as a whole. Then the axis must not be confined to some vague macroscopic scale, but must extend to all scales. So in this form, namely according to the criteria that I called ontology, observer independence, and non-vagueness, it is safe to say that an in-theorized form of realism for the foundations of quantum mechanics might happily be part of the epistemologies of both Einstein and Bell. What's a problem that has been already raised in the preceding talks? The problem is that there is a die-hard and widespread view according to which the main target of the Bell theorem is the infamous local realism, where again in this literature the realism essentially is equivalent to the pre-existence claim, and it's equivalent to what, for example, Giancarlo called determinism. There is a wide variety of terms, more or less equivalent. As I said at the beginning, I want to report some statements about this tendency. The following statements, I would not call them stupid statements, I have to be fair, but they are just wrong. And there's a slight difference. Of course, the first is taken from lectures on quantum theory by Chris Isham. It is important to emphasize that the only assumptions that have gone into proving the Bell inequalities are: for each particle, it is meaningful to talk about the actual values of the projection of the spin along any direction. And second, there is locality in the sense that the value of any physical quantity is not changed by altering the position of a remote piece of measurement equipment. This other instance is taken from the book by Nielsen Chuang, Quantum Computation and Information. What can we learn from Bell's inequality? For physicists, the most important lesson is that their deeply held common sense intuitions about how the world works are wrong. The world is not locally realistic. The world realistic means it's very strange. Anyway, most physicists take the point of view that it is the assumption of realism which needs to be dropped from our worldview in quantum mechanics, although others have argued that the assumption of locality should be dropped instead. Regardless, Bell's inequality, together with substantial experimental evidence, now points to the conclusion that either or both of locality and realism must be dropped from our view of the world if we are to develop a good intuitive understanding of quantum mechanics. Okay, so according to this widespread view, we have both assumptions, realism and locality, which lead to the Bell inequality, so that violation points to the negation of the conjunction. So as Giancarlo recalled, we have an option of what of these two assumptions must go. Further, this is the point where I recall again the Leggett contribution to the debate. If we take seriously that both assumptions are needed to derive the Bell inequality, it makes sense to ask what happens if we try to formulate non-local realistic theories. This is basically the contribution of Leggett and co-workers in the last, say, 10 years. In this framework, a new inequality is derived, which is called the Leggett inequality. And it can be shown that this inequality is violated as well. So that the upshot is that this violation of the Leggett inequality leads to the negation of this new conjunction. Okay? So I take seriously that realism plus locality leads to the Bell inequalities that I know to be violated. So I investigate whether it makes sense to formulate a new class of non-local realistic theories. I find a new inequality which is violated, and this leads as a consequence to the negation of this conjunction. So not only local realistic theories are not viable, as in this wrong view the Bell theory shows, but showing that also this inequality is violated shows that not even this conjunction can hold. So we cannot have even non-local realistic theory. Okay. And again, it's already been said, but it's enough to read the first page of the Bell 64 paper to show that the real point at stake is locality. It's a locality that allows to derive and not to assume at the outset the idea that the subsystems at the source of an EPR pair have definite properties. I skip this. So that, again, as I stress again, the pre-existing properties are not assumed at the outset, but are a consequence of the local assumption. So, with reference to the Leggett and co-workers discussion, the whole enterprise doesn't make much sense if we recognize this very basic and starting point. Here again, I recall texts that have been already mentioned. I just want to recall that this is just a footnote. Yes. It's a shame that it's just a footnote, because a right place to appear would have been in the main text. Okay, so usually Not even philosophers read very much footnotes, not to speak other people. So
I can guarantee you that Bell was claiming that many times.
I'm
when
sure.
discussing with me.
I am absolutely sure. Yeah. Okay, let's skip that. I would like to conclude my presentation with this point. After trying to show why, once again, ill-defined notion of realism has been attributed to the Bell view of physical reality, let's try to focus again on which notion of realism, plausible notion of realism might have been developed in his general epistemological stance. This view is clearly related to his notion of beable. Again, I recall a text that has been already reported. I just add that it is the second instance of judo-like maneuver that we find. The terminology beable as against observable is not designed to frighten with metaphysics those dedicated to real physics. It is chosen rather to help in making explicit some notions already implicit in and basic to ordinary quantum theory. For in the words of Bohr, it is decisive to recognize that however far the phenomena transcend the scope of classical physical explanation, the count of all evidence must be expressed in classical terms. It is the ambition of the theory of local beables to bring these classical terms into the equations and not relegate them entirely to the surrounding talk. Okay, a point that I would like to stress here in connections with the notion of beable that has been already emphasized and stressed as regards its relevance for the foundational contribution of Bell's work is that this notion of beable seems to play also, and in my view this is a very important point, seems to play a sort of methodological role. Why? Because it drives the constructions or the construction or the reformulation of the theory toward conceptual precision and clarity on what the theory itself is about. In this sense, it seems to me that the notion of beable plays a methodological role. It is not just a plausible way to require an ontological import from our physical theories, but it's also a sort of methodological recipe in order to formulate theories with enough conceptual and foundational clarity and rigor. So in this sense, it plays also a methodological role. And in my opinion, this passage from La Nouvelle Cuisine is a good place that illustrates this point. No one is obliged to consider the question, what cannot go faster than light? But if you decide to do so, then the above remarks suggest the following. You must identify in your theory local beables. This is a sort of methodological recipe that goes toward clarity and precision in the construction or the reformulation of your theory. The beables of the theory are those entities in it which are at least attentively to be taken seriously as corresponding to something real. And there is a nice paper by Travis Norsen which deals with the notion of John Bell local causality. Personally, I think that this is one of the nicest papers appeared in recent times on this topic, because he has in this paper a very thorough and precise analysis of Bell's notion of local causality, and in my view, that's why I wanted to put this to your attention. In my view, he stresses this methodological aspect of the notion of beable in an interesting way that should be taken seriously into account. he says that it is important to appreciate that a beable is only a beable relative to some particular candidate theory which posits those elements as physically real and gives precise laws for their dynamics. Thinking in terms of such candidate theories helps us to separate questions about what the real beables are, what really exists out there in physical reality, into two parts. What elements does a candidate theory posits as beables, and which candidate theory do we think is true? The point is that you do not have to be able to answer the second part to answer the first. This is the methodology aspect. It is very safe in reconstructing or formulating a theory to be clear about what the beables of the theories are, even if we don't bet immediately on the truth of the theory. In this sense, the notion of beable seems to play also a methodological role. And basically, this stress on the importance of beables is what motivated what is now known as the primitive ontology approach to physical theory, not only in principle non-relativistic quantum mechanics, but also several different theories. And there is nowadays a growing literature on primitive ontology, on the prospects of this approach, and I just refer to, as a recent example, this paper. Finally, I would like to conclude with few remarks on the notion of beable. The first remark refers to the double role that the adjective local plays when you talk about local beable. Namely that for a beable to be local simply means that we associate to a beable a bounded space-time region in space-time. Okay? So it is perfectly consistent to have a known local theory that posits local beables within its primitive ontology. Well, this is rather trivial, but I just wanted to make it clear for students, for young people. Okay? Of course, in this sense, it is also possible to entertain the idea that you can have non-local beables. So, for example, if you grant the status of beable to the wave function in 3n dimensional space, you are ready to attribute a beable status to a non-local entity.
But for David it will be local.
Yeah, I would like to, this is interesting because I added this, this note, these few lines after the Lev lecture, because in some sense, and perhaps in this sense you might say the same in the Albert case. Okay, in any case, I was finished. Sorry,